Good evening, all. So let's wait for like 5 more minutes so that more students can join, and we'll start the section soon. Okay. Good evening, all. So welcome to the week first program solving session for the course Matlab-Based Programming Lab in Chemical Engineering. So first, what I'll do is we'll quickly discuss what we discussed this week, so that in case you have any doubts or something, you can ask me. And after that, we'll try to solve some problems. Like it will be similar to the ones that you get for your assignments, so that it is easy for you to solve. So this week we'll be dealing with the CSTR. So in CSTR, this is the diagram that will be, this is a problem that will be assigned that we are doing this week. So starting, just give me a second. Yeah. So starting, you have like a feed flow rate, which is given by capital F, and CF is a concentration of your the chemical in your feed, and TF is the temperature of that. Okay. So F, CF, and TF, these are inlet conditions. And then, in CSTR at every point, since there is continuous mixing, so the concentration will be same throughout throughout the reactor. And also the outlet, whatever outlet concentration that you will have will be same as the concentration that is inside the CSTR. So inside the CSTR, you can get the concentration given by C, temperature given by T, and the temperature given by V, and the rate of the reaction. Okay, R is referred to the rate of reaction that is given by small letter R. That is exactly same as outlet condition. So you get F, C, and capital T. Okay, so this reaction that we are dealing here could be an exothermic reaction or an endothermic reaction. Okay, depending on what kind of reaction we are having. So then what we do is we are having a cooling jacket. It could be a cooling jacket or heating jacket. Now, the whole thing is we'll have a flow rate of Fj, which is the jacket fluid's flow rate, and which is having a temperature Tj. Okay. And what will be happening is there is heat transfer happening between the coolant to the reactor or reactor to the coolant, depending upon which is having the highest temperature. Okay, depending on that, we'll have the heat either transferring from one side to the another. And then we have the outlet also as FJ and TJ. So basically, here there are two kinds of equations that is governing this process. One is the mass balance equation, that is basically the concentration equation we'll have. That is F by V is F is a flow rate, and V this is volumetric flow rate. Okay, so that will be volume divided by minute or second, and then divided by volume means you will be having the empirical unit of this will be 1 divided by time. And then what is this? CF minus C. CF is the initial concentration and C is the final concentration. So CF minus C divided by T means this is actually referred to, this term is actually nothing but the change in concentration, right? And then change in concentration is caused by the reaction. So the reaction here, we are considering a first order reaction. So it will be pretty straightforward. You will have a reaction rate constant, which is multiplied by the C. So it can be calculated as Kc, where K could be a function of temperature. So in this case, we're considering K as a function of temperature. So nothing but K will be equal to K0 e raised to minus E by RT. Okay, that formula which we have already learned in our basic chemical engineering courses. So this will be the first equation that we have. Change in concentration is due to the reaction. So this will be the first equation that we'll be dealing with. And the next equation is the energy balance. So basically you will have the temperature as a variable here. So when we have temperature as variable, first let us look at the reactor temperature. Okay. So first inlet temperature is TF and the outlet temperature is T. So the difference is TF minus T. And also this is the volumetric flow rate divided by the volume. Okay. So this is the change in temperature with respect to time. And now we have like since there is a heat of the reaction, right? It could be exothermic or endothermic. Exothermic means delta H will be negative and endothermic means delta H will be positive. Okay. So it could be exothermic or endothermic. So depending on that, and that also depends on the reaction rate also. If it's a very highly reactive reaction happening, then you will have high heat transfer that is happening, right? So that is why we have this equation minus delta H, which is the enthalpy of the reaction divided by rho Cp multiplied by R, which is the rate of reaction. This is the quantities of the reactants that is there, okay? Rho and Cp. Then you have a jacket fluid that is flowing through the coolant jacket here. So that will also have a change in temperature that is happening, right? So that will be happening exchange with the input in exchange between there is like a heat exchange that is happening between the coolant and the reactor. So what is the temperature difference that is driving this? That is the temperature difference is Tj or T minus Tj. Okay, difference of temperature that is inside the reactor with respect to the coolant temperature. Okay, so the temperature difference that is driving this heat transfer is T minus Tj, and then there are other constants that is happening like the heat transfer coefficient and everything. So A is nothing but the cross-sectional area. B is again the volume of this reactant that is there, and rho Cp that is the quantities of the that is inherent properties of the reactor fluid. So right now we have like two equations to solve. And we need to understand that we have already in the previous case, in the previous week, what we dealt with was like Coolbrook relation. Okay. So in Coolbrook relation, we basically had just one friction factor or the friction factor as the only variable. Okay. But in this case, we have two variables. One is we don't know what the reaction temperature is, and we don't know what reaction concentration is. So we have like two equations that is governing that. This is for reaction concentration and this is for the reaction temperature. But these two are coupled. How is this coupled? So if you look at this rate of the reaction R is nothing but Kc. But again, K is dependent on temperature. Okay, so that is dependent on this. Okay, so this equation you cannot independently solve because R depends upon the temperature. Okay, now coming to the second equation, this also you can't independently solve because R is nothing but Kc, right? That is concentration, rate constant you multiplied by the concentration of the reactor. So again, it's dependent on the C here. So right now what we have is we have two simultaneous algebraic equations. They are non-linear equations, obviously. These are not linear relationships. And they are coupled equations. Coupled equations means a result. Like you have to solve this simultaneously. Like together you have to solve it. Because depending upon the C, if a concentration changes, both the equation changes. Both the values of the equation changes, and if same with temperature. If there is a change in temperature also, but the value of both this equation changes. So this is like simultaneous algebraic equations which are non-linear and coupled. So today in today's class, we'll be trying to see how to solve such systems. So just give me a second. Okay. So these are the sub questions which we'll be trying to answer. Okay. The first sub question is examine the effect of initial guesses of concentration and concentration and temperature in the reactor on their steady state values. That is concentration and temperature of the reactor. So basically, you have like a concentration. C and T need to be found out at steady state. Again, what is steady state? So if this temperature, okay, if this so basically what happens is when you start a reactor, okay, imagine you have just started the reactor and you have like a coolant fluid that is starting, that has been started flowing. So what happens is initially this whole system will not have attained an equilibrium temperature or equilibrium concentration. Okay, because the reaction has just started and the coolant temperature is having starting some other temperature value. So now what happens is, so initially there is like a change with respect to time. Okay, as time changes, both the concentration and temperature changes. But once the system reaches equilibrium, what happens is the coolant temperature remains constant. So there is no change with respect to time. Okay, that is called a steady state. If so, that is why if it was not steady state, what will happen is instead of the zero, you will have a d by dt term. Okay, d by dt where t is nothing but the time. You will have in this equation, we have to account for the change with respect to temperature also. Okay, so that is why whatever we are dealing. So these two questions are basically for steady state, that is the change with respect to temperature is zero. Okay, now what we have to do is imagine that there is an initial value for C and initial value for T. Okay, let us imagine that what will be the steady state condition, like basically what's the steady state value for C and T. Okay, so that is the first part of the question what we will be dealing with. Like, can you just guess what kind of method should we be using in MATLAB? So basically in MATLAB, what happens is in steady state equation solving means basically this equation that we have is a steady state equation because there is no d by dt term. Again, in this equation, this is also a steady state term because there is no d by dt term again. So basically to get the steady state C and steady state T, you have to just solve these two equations together. Okay. And again, highlighters, these two are nonlinear equations. When you have to solve a set of nonlinear equations, okay, what do? We use fsolve. Okay, fsolve is an inbuilt MATLAB solver that can deal with solving nonlinear equations. Okay, so we'll be trying to use fsolve. And also remember in fsolve, we saw it last week also. Fsolve requires an initial concentration or initial variables has to be given. That is, if you're trying to solve for concentration and time, in fsolve, you have to give an initial concentration value and initial temperature value. Okay. Once that is given, these two equations are solved and you will be getting the steady state concentration and steady state temperature. So that's what we'll be doing first. But before that, let me just show you the initial guesses that we have. So different initial guesses have been given for C and T. Basically, in this equation, C means nothing but Ca. A is the reactant name. Now we have to do it for all three gases. So the first guess is the concentration of the reactor is 9 kilomole per meter cube and temperature is nothing but 27 degrees Celsius. Again, guess 2 is 5 kilomole per meter cube Ca and temperature is nothing but 77. And guess 3 is the Ca is nothing but 1 kilomole per meter cube and the temperature is 177 degrees Celsius. Okay. So these are the different initial guesses to be used. Now we have the other parameters. So the other parameter is basically F by V. That is the flow rate divided by the volume. As I said, the unit will be 1 divided by the times unit. So that is given as 1, 1, 1. K is nothing but the reaction rate constant. So that is given in this value. Delta H is the enthalpy of the reaction. Again, we have three cases. And E is what was E? Have we used E anywhere? Okay, E is the activation energy because we have the reaction K equal to K0 E raised to minus E by RT. So this is the activation energy that is there. Rho Cp we have already discussed, that is the property of the reactants. Again, that is given. TF is the initial temperature. Okay, initial feed temperature. That is also given to be three conditions. CAF is the initial concentration, okay, initial feed concentration. UA by V is the heat transfer coefficient. You will be getting it like this, 250, 150, and 750. And TJ is the jacket temperature, okay. So these are the different reactor data. What is the aim? We need to find out what is the reactor concentration and reactor temperature given a steady state and given an initial guess. Okay. So first I'll just show you the code and then we'll explain like step by step. In case you have any doubt, please do stop me and ask. Hmm. So this is the code that we have written for this. I'll just explain line by line. In case you have any doubt, please to stop me and then we'll discuss. Okay. So uh, am I sharing the MATLAB? Okay, fine.
Yes.
Yeah, thank you. So to begin with, you will have you have the basic commands for clearing the screen, clearing the workspace, and closing all the figures. Then you have something called as global variables. Okay. So if you are declaring a variable, okay, that's basically what we have. By default, what we have is a local declaration. That is only in the snippet of the code where we have declared the variable, you can use it. Okay. Outside the snippet, that variable doesn't have any, you can't access the variable. Okay. But if you're using global variable means it can be used anywhere in the program. You'll understand that slowly. So these are the kind of global variables that we have. This is basically the different parameters that we saw in the table. Okay, K0, delta H, rho by CP. Okay, that is rho CP, that is UA by V and all those things. Okay. Now let us consider there are three guesses. Okay, there are three guesses. First one is for the concentration and the second one is for the temperature. So in guess one, concentration guesses, initial concentration guesses 9 and the temperature guess is 300. Similarly, you have like three different guesses that is happening here. Now let us do for parameter set 1. Okay. So in parameter set 1, this has been tabulated from the table. But one thing, yeah, yes, you have a question?
Yeah, so okay,
Yeah.
how do we guess a value? Like, why can't we use any numerical methods for guessing it? Like, taking two upstream values and then dividing, like interpolation or Newton raphson, something like
You're
that.
talking about which value, the guess value or this
Yep,
value?
yep. About the guesses value. So like,
The guess
we
value,
may not know,
obviously,
right?
you can take it from anywhere. If you have done experiments or if you have prior knowledge, you can take it accordingly.
No, no, no. I mean to say, okay, yeah. So how do we validate that the guesses that you have taken that are right? Like, okay, you perform the code and then
You
you get it, but
Yeah,
yeah.
you can see Fsolve. What it does is, depending on your initial value, you get different values. Okay,
Yep.
you might be doing it in experimental setup, right? So obviously, from or else you can take it from the literature review or something. You'll be getting how close, you'll be getting an idea of what a steady state concentration, steady state temperature is. Then to get that, you have to give a value that is close to it. Okay, that is when
Yeah.
Fsolve will take you to the actual value.
Yeah. Thank you.
Okay, yeah. So that this requires prior knowledge, basically. Or else you can
Thank you.
just keep doing trial and error and probably you what will happen is how multiple guesses you give, you will end up having a single steady state concentration, single steady state temperature. But that totally depends on what kind of system you are working on.
Yep. Yeah. Thank you.
So now the parameter set coming here. Understand that this is very important because there are so many parameters. You have to be very careful with the units. Okay. So if there is units like if there are something in hours, something in minutes, make sure that you bring everything into the same scale. Okay. So here you can see the temperature has been converted into Kelvin and all those changes has been done. So make sure every unit that you're applying is it's correct. The unit wise it is correct. Now what we have is we are trying to solve. So the keyword for solving fsolve is this one. And then what do? You give a function name. Okay. And the function has to be given with this at symbol. At symbol means it's called as an anonymous function basically. But you're just telling MATLAB, okay, this is the function that I'm trying to solve. Okay. That's what fsolve identifies this as. And then you give an initial guess for the variables in that function. Now let us see what this function does. That is CSTR func. Okay. What is the CSTR func taking? So CSTR func is here basically. CSTR func will take an initial value x. Okay. And again, you can see there is like variables here k0, h, and all those things. Okay. It's again declared as global. And now we have the rate. So the rate, as you know, in this equation, we have like two equations here, right? Just a second. So we have, yeah. So we have like two equations here. with R. Okay, so first we have to calculate R. How is R calculated? R is nothing but K multiplied by C, and K is nothing but K0 e raised to minus E by RT. All these equations are given to us. Okay, so we can first find K0 and then we can find R so that we can directly substitute into this. So here we'll have X. Okay, remember in the X is actually a vector which is having two values. The first value will be concentration and the second value will be temperature. So first let us calculate the K0 e raised to minus E by RT. T is what? T is the second variable in the X vector. That is why it is given as X2. Okay, so that is multiplied by C. C is nothing but the first variable in this vector X. So first you have calculated the rate to be like this, K0 e raised to minus E by RT multiplied by C. Okay, so first we have the rate and now we need to compute what are the two equations. What are the two equations we are looking for? One is F by V, CA, the field minus CA multiplied, okay, CAF minus CA minus R rate. So basically you can see that here. So this will be the equation. C F by V. You have C F minus C and R has been already calculated. So now that is the first equation. Imagine that, so another thing you have to be keeping in mind is that whenever we are solving F solve, the equations that we are writing, okay, it has to be equated to zero. Okay, in case imagine that you have a whole equation and then it is written equal to 2. Okay, then you have to bring 2 to the other side so that you can write the whole equation minus 2 equal to 0. Then that equation that we have written minus 2, that whole thing becomes the equation that you're trying to solve in F solve. Okay, always the equation that you're trying to solve in F solve must be equated to 0. Okay, if it is not equated to 0, rearrange it and try to equate it to 0 and solve for the rearranged equation. So I hope that part is clear. So now this is the second equation. We have TF, again the second parameter, which is temperature. Then we have the multiplied by rate. Uh, yeah. And then this is T minus TJ. So that's the second parameter in X. So this will be the basic output. And you know that when you give output, that is a functions, okay, then it has to be also a column vector. So this is the first row, first column, and this is second row, first column. Basically, you have one column and two rows. First row will have the first function and the second row will have the second function. So now we have two equations to solve. Now F solve, what it does is it directly creates this guess 1, guess 2, and guess 3, and it calculates the values for you. Now we are actually trying to tabulate it well. So what I do is, so from the solution, the first value, okay, the first value, index 1 will give me the concentration. So here also the first index will give me the concentration. And here also the first index will give me the concentration, right? So what you do is I just put them together in an array. And I'm also trying it to round off so that there is only two significant digits. So this is how you round off in Matlab. You can see the command to yourself. Now again, the second one is the temperature. So in temperature also, it has to be the second value in the solution. So that is xol 1 to the second index, again the second index, again the second index, again rounding off to two significant digits. Okay. Once you have rounded off that, then we create the table. Okay. For the table, what you have to do is you have to give the, just a second. Yeah, you have to give three, basically there are three things that you need. First, for guess 1, guess 2, guess 3, you need to identify what's the concentration for guess 1 and then the temperature for guess 1. Then coming into the guess 2, we have the temperatures, we have the, we have the concentration first and then the temperature. So likewise, to make a table in MATLAB, what you have to do is you have to enter each and every column of the table. So this is the first column, which will be the guess number. CA solve 2 will be the second column, which will have the different values of CAs for different initial guesses. And T solved also, you'll have different values of temperature for different initial guesses. So that's how we create a table. So let me just run it. So finally, what you'll be getting is, remember this was parameter set 2, okay? For parameter set 2, for guess 1, I'm getting CA to be this and T solved to be this. So these are the three different guesses for parameter 2. Okay, did we actually finish the problem? Not yet. Because in the question, it has been clearly mentioned that we have to do with three set parameters. So what you have to do is, so for one set of parameters done, now go back, make the changes in this parameter set so that it fits your second model. Okay. And again run it, you will be getting the CA and T solved. Again go back. Now you erase the parameter set 2 and again write your parameter set third. And after that, you try to solve it and then you will be getting the values for C and T for the guess 1, guess 2 and guess 3. Okay. Is this clear? Any doubts?
Yeah, it's clear. Thank you.
Yeah. Now, so this first part of the question is done. Now coming to the second part of question. Examine the effect of feed temperature and jacket temperature. Uh, Effect of the feed temperature and jacket temperature on the steady state concentration and temperature of the reactor. Okay. So here in the early case, we had kept the feed temperature and jacket temperature to be fixed. Okay. Now what we're doing is we need to vary the feed temperature and jacket temperature and see what is happening to your steady state concentration and operation and temperature. Okay. Just a second. Let me just clear this first. So how do you do it? Just once more, I'll just show you this part one. So in part one, TF was fixed, feed temperature was fixed, and TJ was also fixed to a certain value. Now you can't be fixing it, but you need to try to vary that so that your steady state temperature and steady state concentration keep on changing. Okay. Now coming to part two, first we have all the basic equations, and then we are declaring the global variable as we did before. And now we have the set of parameters. The parameter set 1 is there. Similarly, your parameter set 2 and set 3 has been given to you. But first, let us do for set 1 because rest of the steps you can just keep repeating what you have done for the set 1. Okay. Now we have the reactor. Okay. So first understand that what we have to understand is the effect of feed temperature and jacket temperature on steady state concentration and temperature. Feed temperature and jacket temperature. So we have to study the effect of that. How do we account for that? First, we say let the reactor temperature be equal to from 300 to 400. This could be any value. Okay. Now, what we do is we give this T reactor to this CSTR curve 2. We'll see what is happening in this function. So this is CSTR curve 2, which is having a temperature, initial temperature that is given. Initial temperature is nothing but the reactor temperature that has been given. Okay. Now, what we have is 1 to the length of T vec. So basically, T vec is here. It has temperatures varying from 300 to 400. Okay. So for each element, 1 to length of temp vec means from index 1 to whatever is the last index of the temp vec array. So that will be the number of times the loop will be running for you. So now, it's just a second. Yeah. So now we have a loop running, and then you have the temperature that has been given to you, right? That is the reactor temperature has been given to you. Okay, that will be the I will keep on changing depending on how the number of loop you had. So now we have the capital T. Now we can compute what is the rate constant. What is the rate constant? Rate constant is R. Rate constant R is given as KCA, where K is nothing but K0 E raised to minus E by RT. Okay. So that's what exactly we are trying to do. K equal to K0, which is already a parameter given to us. Exponential minus E is also a parameter given to us. R is there and T we obtain from here. Okay. T first it will take value for 300 and then it can go up to 400. So this is the first value of T we take here. So we have computed K. Once you've computed K, then we need to compute what is the rate. So rate will be what? Rate will be this K constant multiplied by the CA. Okay. K constant multiplied by the just a second. I think this is not required. Sorry. This is a rate equation. Okay. So before that, we need to find the CA also. So for finding CA, what do we do? Just a second. Just a second. So we have CA given as V by F, CA divided by V by, sorry, F by V, K. We will F by V plus K. You will have a doubt from where this we got this equation. Okay. Yeah. So we don't know what the reactant concentration is. Okay. But we know what should be CAF is the feed concentration. So feed concentration we already know. Okay. Feed concentration we already know. Now V by F by Vk. So where did this reaction come from? You can rearrange this equation like this. So this is the first equation that we have. Now you'll have to rearrange in such a way that you get the reactor concentration. So that is, you open the bracket. Now group all the terms that is having C here. So that will be C multiplied by F by V plus K equal to F by V CF. Again, bring this down. Okay, then what you'll have is you'll have a concentration for you'll have a representation for the reactor concentration. Okay, sorry. So that is what is given here. Okay, Ca F by V is known, CAF is known, F by V is known, and K you got from the temperature. Okay, and now we have the rate of the reaction, that is K multiplied by Ca. K has been calculated here, Ca has been calculated here, and so this is a final rate. Okay, so now first rate has been calculated, then you need to find the other terms. Okay, so first understand there should be like two out. So we need to identify what is the uh, just a second, jacket temperature. Okay, so that's what we were intending to do first. First, we need to find the jacket temperature, the effect of the reactor temperature and reactor concentration on jacket temperature. So first, we are doing it for the jacket temperature. Okay, and then we'll do the next part of the question later. Now, rate is calculated. Now we have to calculate term 2 and term 3. What is term 2 and term 3? So here. So what happened is this is the whole equation. Okay, we need to find what is the jacket temperature. So we have to rearrange this equation so that the whole equation can be written as Tj is equal to something. So now this is when you rearrange it, this is what you will be getting. Tj is equal to T plus V by F delta H by rho Cp R U by A divided by V rho Cp T minus Tj. Okay. Now you have to code this equation. Okay. So for coding this equation, you know this is nothing but this part is nothing but it is a term 2 and this is nothing but term 3. Okay. So right wise you will have to arrange it in MATLAB. So term 2 is given, term 3 is given. Okay. Imagine that here the just a second, let me just confirm the question once again. Estimate the effect of feed temperature and jacket temperature on the steady state concentration and temperature. Okay. In the reactor.
Hi.
Yeah, yes.
So I'm not sure of this. In steady state, the temperatures will be constant, right? Like the change in temperature will be constant, right? For
The
feed
change in
and
temperature will be constant. Yes.
yeah. So yeah. So we don't know the temperature of jacket and the temperature of the reactor, right? So
No, no,
uh,
no.
I
So that
assume
is,
that
yeah.
yeah. Sorry. Yeah.
No, no, you can go on. Just complete your question.
So assuming that taking a like term one, term two, term three, and then correlating three ones will be getting the temperature, like the values of temperature of feed and jacket, and then
Yeah.
uh, yeah. So yeah, thank you. I was just confirming that whether my
Yeah,
hypothesis was
yeah.
right or wrong.
Yeah, right. What happens is like it's like a what you say, it's like a egg and hen problem. Okay, so you don't know what both the temperatures are. So that is why we assume one thing. We assume we know the T reactor. Okay, so now we go towards the getting the TF. Okay, that is
Yep.
a feed temperature. So now
Yeah.
what we have is we have given data the input. So we
Yeah.
calculate the k with the with the k we get let me just not save it. Let's see. Yeah. Now we have calculated the T has been already given to you. Reactor temperature, we assume that okay, we know it. For a certain value, we know it. Now we have
Yeah.
for that we calculated K and then we calculated Ca for that. Okay, this is how did we do it? We rearrange the first equation. Okay,
Yeah.
now we need to calculate the Tf, which is unknown to us. Okay,
Yeah.
so for time being, actually both Tf and Tj is unknown to us. Tf is the feed temperature and Tj is the jacket temperature. Both are unknown to us basically. Okay,
Yes.
but
Yeah.
the thing is, we will have to fix at least one of them. So if you look at
To get
this,
the other one. Yeah.
yeah, if you look at this parameters table, they have given you default value or like see, TF is being given default value 25, 20, 25. TJ is given 25, 25, 25. So in case in your whole problem, you have to fix a certain quantity. Okay, then you can fix it to be this 25 degrees Celsius, which will
Okay.
have to be converted into Kelvin. Okay, so
Yep.
that's what
Yeah.
we are doing. Right now, we are doing it for the TF, that is a feed temperature. So what we assume that TJ is held constant. And what is
Yeah.
TJ? TJ, if you go back, you'll see that is, sorry, it's parameter
20
number.
like
Yeah, 25 plus
yeah.
273.
273.
Yeah.
Thank
So
you.
now you have the term 3 that has been calculated and term 2 and term 3 that is calculated, right? Now you have everything else calculated here and then you will get a value for TF. Okay, so this is you're assuming one value and you're going like in cycle. Now what you get is you get for different reactor temperature, you will be getting what is the feed temperature, right? So that's what we are trying to plot. So you will be getting you input is your reactor temperature and the output is your feed temperature. Now what we'll be doing is we'll be plotting this feed temperature as a function of reactor temperature. Okay, so that I'll just run and show it to you. Sorry. Okay, this is something, this is how your behavior looks like. Okay, given the, this is TF and this is T. Is my X and Y axis correct?
Yeah.
I don't think so. Just a second. Maybe my labeling is wrong. That's what I was thinking. No, no, that's correct only. So X label is TF and Y label is T. Okay, I'll
Yeah.
just run it again. See, it can be done the other way around also. Right now, what we did is we assumed we know the reactor temperature and then we calculated the feed temperature. You can do it the other way around also. You assume that you know the feed temperature and then you can calculate the reactor temperature because you have to just rearrange the same two set of equations, right? So that way around also can be done. Right now, what we did is we assumed that the reactor temperature because lot of your equations are dependent on your reactor temperature. For example, rate of the reaction, all those things are the R, everything is dependent on T. So we assume we know T and then we found TF. Okay. This can be if you want to plot TF on the y-axis and T on the x-axis also, you will get a similar behavior kind of a graph.
So how do I
Now,
know the steady state temperature? Like, is it between 300 and 310 because there's a curve over here?
this is not a steady state condition, right? So in steady state
No, how do I
condition, yeah,
find the steady state condition from this?
okay, you'll have to plot and finally you will see the value don't change for the slope doesn't change for a while.
Got it. Thank you.
Yeah. So that's about it. Now again, another part of this, so only this has been discussed in the video lecture. So that is studying what is the effect of T on TF. Okay, similarly, if you look at their problem, you need to find TJ also. You need to understand how the behavior of jacket temperature also is changing. Just a second. See, we have to study the effect of feed temperature and the jacket temperature. Okay, and so for that, what you'll have to do is instead of in the whole function we had, right? We wrote the function for calculating the feed temperature. Now we'll have to write the function for calculating the jacket temperature. I'll just quickly show you how it is done. Uh, just give a second. See, how it is done is this part of the program remains the same. Okay, let us assume there is an initial reactant temperature. We know the T, and from T you can calculate this K. You know the C. So this equation is calculated. Okay, we know the C from here. Okay, this part remains the same. Now, this is where we rearranged and we got value for TF, right? Now you can, what you assume is, imagine that TF is given and TF from the table, you know it is 25 degrees Celsius, right? So take that guess for TF. Now what you do is you rearrange this equation for getting TJ. So that is this equation. Okay, now that term 1 and term 2, wherever we added, instead of writing this equation, what we do is this. Here, the only unknown is Tj. T we initially assumed in the beginning of our program itself. TF, we take the default value, which is 25 degrees Celsius, convert it to Kelvin. Okay, rest everything. Reactor R is also known for a particular temperature and concentration. Okay, is this part clear?
Yes.
Yeah. Uh, so actually, I have like wrote it here. Yeah, so this part of the code I have just written the same code only. I've repeated it. So this is for TJ. See, this expression has changed. So sorry, here you have to give TF as a constant. So this expression has changed. It's different from the earlier one. F by V, instead of that, you have this UA by V rho Cp. Okay, so this is how you do it for TJ. Now, what happened is in both these cases, what did you fix initially? You fix the temperature of the reactor, right? And now you can do the other way around. Why don't you fix the concentration of the reactor? Okay, when you fix the concentration of the reactor, you have two equations. One is from KCA, you will be getting, so you can do the BAL calculation and you can find the temperature of the reactor. Okay, there's an equation like this, right? So that will be a more difficult route because when you start with temperature, it's pretty straightforward. So yeah. So this is the two equations. One is for the feed temperature, and other is for the jacket temperature. Now going part to the third part of the question. That is, develop a 3D plot to examine the 1 minute. I just missed something. Yeah. So should I run this for you? Like, do you need this code or something? Or maybe you can take it from the. This is the
That's
third
fine.
part of the code. This is for the jacket.
We can run the code and discuss what happens in the
Yeah.
code. Like run the code and look at the graph.
Yeah, the behavior is actually same. You have to look at the values properly. The behavior remains the same. You'll have to plot the graphs together in a single plot and see how it is different.
Yeah.
Mhm. Yeah. Maybe for curiosity, we'll just do one thing. Run this whole. Oh, basically what happened is. Yeah, you have two behaviors. The first one, what I did was for the feed temperature, and next one is for the jacket temperatures. Okay. The like still it has been increasing, so it will still take time for it to reach the steady state. Now going back to the third part of the problem, that is develop a 3D plot to examine the effect of jacket temperature and space velocity on the steady state temperature in a reactor. Okay, so in this we are not doing anything so different, but what we'll be trying to do is we already have a code that we have written for the second part of the program. We'll try to see from that, can we just try to see what is the effect of jacket temperature? Space velocity is nothing but F by V. Okay, and on the steady state temperature, that is the T of the reactor. Now, let's see that. So the whole part remains the same. We have the global parameters here. Okay. One important thing is why we keep this global parameters like this is because you know that in some case we are declaring TJ in some part of the program, right? TJ I fixed it to some into some value here. And when I ran the second part, I'm fixing TF, right? So what happens is when you're making it global, in any part of the program, you make a change for this variable. What happens is that change will be reflected even outside that function. So even if you're declaring it here or maybe like somewhere else in this 2A or like the second part of the program, since it's global variable, if you make a change, that will be reflected everywhere. Everywhere, if you're fixing TF is equal to 25, then everywhere in the program, whichever code you're running here, since it's a global variable, the value will be 25 itself, fixed for you. Okay. So this is like when you know that you have to use the same variable like in different parts of the program, declare it as global so that you don't make mistakes. So now coming to part 3, we have all the global variables and we are doing it for the parameter set 1. Okay. Now what we do is we need to have the effect of f by v value also. So far what we did is we fixed the f by v value. So f by v, we had a default value, right? So here the value is 1. So far our whole calculation, we have only done it for f by v equal to 1. So now this is the space velocity. We need to do it for different space velocities. So what do? You make the space velocity to be changing from 0 to 1 in 20 equal intervals. So that's what linspace does. You will have values varying from 0 to 1. Okay, you'll have 20 values and then there will be 20 values and the interval will be automatically calculated. What step size should be taken for getting like 20 equal intervals. So that will be calculated by linspace itself. So you'll have 0 to 1 values vary. Now you have the temperature T reactor also. Okay, T reactor also you had from 350 to 400, you have like 70 values, just like we did earlier. Now what we do is, earlier we used the CSTR curve, this command only once. Why? Because we had a single F by V value and the only input you had is T reactor. Okay, so that's what we did. We only used it once, right? Now you will have to put it in a loop so that you can run it for different F by V values. So that's what happens here. So what happens? F by V, there are different values. I put it in a loop. And how long is the loop? The loop runs from the first element to the length of this F by V vector. So that is, it will run so that it can get access to each and every F by V value. So that is the actual F by V. Remember, this is the global variable. So in the first loop, when I'm saying F by V equal to 0, everywhere in the program, F by V will be 0. Now again in the second loop, F by V will be some 0.1 or something. Then everywhere in the program, F by V will be equal to 0.1. Okay. So that is the advantage of using global variable here. Now F by V, I'm declaring it has to be the first value of this vector. Now I'm running the CSTR curve 3. Now what happens in the CSTR curve 3, if you go, wherever F by V is required, it will take the first value. See, wherever F by V is required, it will take the first value. Now again, when I am when I'm using the second element of the F by V vector, everywhere F by V is there, it will be taking the second value and so on, it will go on. Okay. So now for a specific F by V, we ran the same command and you get the jacket temperature. So that's the jacket temperature that we get here. Now what we have to do is we have to plot it together. Just a second. Yeah. So for plotting, what do we do is we have to plot three values here. So that is a three-dimensional plot. That is why the keyword is plot 3. So in usual plot, we only have the x and y values. Here you'll have 3 values to be given. One is the jacket temperature. So I'll just run this code once. 1 minute. Okay, this is something how the plot looks like. This is the jacket temperature. It is having 20 rows and 7 columns. Okay, let's see why it's so. 20 rows means each row corresponds to a F by V value. So you can see here, the size is 20 rows and 70 columns. 20 rows means each row corresponds to the each F by V value, and each column corresponds to a particular T reactor value. So we have 70 data points. So that is why your TJSS will be a 20 by 40. Now what we are trying to do is for a single F by V, what will happen? So that is we will have to take row wise. So that is why we have the row number I and the entire columns. Okay. So you're taking the first row, which is corresponding to the first F by V value. Now you know this F by V vector, the first value. This is scalar quantity. Okay. So plotting, you need to make it into a vector. So for that, what you'll do is this has having 70 entries, right? The first row has 70 entries. So you'll have to make this vector also of the size, same size. So for what do? You multiply it by a ones vector, which is having 1 row and 70 columns. And then you multiply it with the scalar value. So now what will happen? The initial value is 0, you will have like 0, 0, 0, 70 times. And then you have the T reactor. T reactor, let us see. It is already a 1 by 70 vector here. Okay. You have the T reactor. So that's how we plot it. Now I'll just, okay. Again, I've run this code here. So this is how we will get it. So the same thing, you can do it for different set of parameters. Okay. Any doubts?
No.
Okay. Now it's almost an hour. So what we'll do is we'll move into the problem solving sessions. So what I'll do is I'll just give you a problem and I'll give you like 2 minutes or more than that, depending on the level of the problem. And then if you have the answers, just please put it in the chat box. And then we'll discuss the answer. So just don't unmute yourself and tell the answer. Like there will be people there are other people in the live session, and also there will be people who will be hearing the recording. So just give like 2 minutes and give the answer in the chat box. And one more thing, these questions are taken from the previous assignments that is given in the NPTEL sessions. So you can expect such kind of questions for your assignments and also for your exam. Yeah, so in a diabetic CSTR, so diabetic means in the system what we had, the CSTR what we had right now, we had like a coolant jacket. Okay, so there is a heat transfer happening between the coolant fluid and the reactor fluid that is happening. So there is no mass transfer, but there is only heat transfer. So it's the opposite of adiabatic. So we have a diabetic CSTR. In that term, in this, what does steady state imply? Okay, so the correct answer is answer B, and I think many have answered it right. So yeah, so that is the temperature and concentration profiles remains constant over time. Okay, so that is a definition for steady state. Now moving on to the second question. I'll give you 2-3 minutes. So the answer is B. So we have like a diabetic CSTR in steady state operation. The inlet concentration is given as 1 mole per liter and the flow rate is 4 liters per minute. And the reactor volume is for 40 liter. And the rate constant is given by 0.2 meter inverse. Now we have to find the residence time. So the residence time tau, the formula is pretty simple. That is V divided by the volume divided by the volumetric flow rate. Okay. So V is the volume, that is 40, divided by the volumetric flow rate. Remember, this flow rate has to be volumetric, okay, not the mass flow rate. If it's a mass flow rate, then you will have to calculate it using the density and convert it to volumetric flow rate. So that is 40 divided by 4. The answer is 10 minutes. Yeah, all of got it right. Now the next question. In contrast of a diabetic CSTR, the term diabetic refers to there is no heat exchange with the surroundings. Okay. So, so there is no heat exchange with the surroundings. There is only within the system there is heat exchange. And yeah, the next question. I've got different answers. So here in the steady state operation, the diabetic CSTR, which variable is directly influenced by the heat transfer rate. Okay, so that is the reactor temperature because as I said, if the reactor temperature, if it is higher than the coolant temperature, so likewise there will be a change in the heat transfer rate. Okay, it could be higher or lower. Depending on that, there could be like heating of the reactor fluid or cooling of the reactor fluid. It depends. So it's a reactor temperature. So next is a max question. So you'll have to do it in MATLAB. So even if you don't have, like if you have MATLAB open right now, we can try to solve it and then let me know the answer. Otherwise, please take a pen and paper and try to write the functional form of doing an F-solve and write the small function that you'll be trying to use it for F-solve. Anybody with the answers? So you'll have to write an fsolve function. Just give me a second, I'll share Matlab. So for that, first you'll have the initial guess that is 2, 3. And then you'll have to use fsolve. You have a particular function with an initial variable, initial data set that is at x0. Now you're just printing the solutions. So before that, we'll just see what the system looks like. So the function name is my system, and it takes in like two variables, x1 and x2. So first, I'm just declaring it to be the function vector to be 0, 0s. Okay, if you don't do this, it's also fine, but better you declare it to be 0. And then you enter the first function, that is 3x1 minus x2 minus 2. Okay, why minus 2? Because this was your equation. And for fsolve, you have to always use a function like which is equated to 0. So you have to bring this 2 to other side, this side, so that it becomes minus 2 and equal to 0. So that is your first equation. And your second equation is 2x1 square minus x2 equal to 0. So that is your second equation. Now we give it together to the fsolve and let us look at the answer. Okay. Uh, okay. The solution was found due to some other stopping criteria. Some gradient criteria. But anyways, the answer you're getting is x1 equal to 0.7500 and x2 is equal to 0.6875. You might get a better answer. You might get a proper solution if you are giving a better initial guess, but that is okay. Right now, this is the solution that you're getting for the given initial guess. Okay. Now, moving on to the next question. Yes. So, what is the answer for this question? For a first order reaction A giving B occurring in a diabetic CST, the steady state concentration of A is determined which are the following parameters. You know the steady state concentration, that is Ca. For a first order reaction, you can calculate as Ca0 divided by 1 plus K tau, where tau is nothing but V by F. So it depends on all of the above. It depends on the initial concentration. It depends on the flow rates because that's what the residence time depends on. It depends on the reaction rate constant. So it's all of the above is the answer. Now the next question. This maybe you can just use, if you have MATLAB, just use the help Jacobian. Jacobian is a function that you will be needing to use run this. There is a Jacobian inbuilt function. Okay, just try for yourself and then we'll discuss the answer. Any answers for this? So the question is for solution of a system of nonlinear equations numerically, it is important to determine the Jacobian of the vector function, which is a matrix of partial derivatives. So the matrix of a second derivatives, okay, this is called as the it's called as like a Jacobian function. So then basically, sorry, the partial derivative is called the Jacobian function. So if you are taking like you have like Hessian matrix and similarly you have like a Jacobian matrix. And now determine the Jacobian of the following vector using the Jacobian inbuilt function in MATLAB. So what we'll do is we'll quickly move to MATLAB. And first what we'll do is we'll type help Jacobian. So this computes a Jacobian of a scalar or a vector f with respect to the vector x. Okay, x has to be the variables and f will be the function value. And the I comma jth entry of the result will be dfi. That is the ith functions partial derivative with respect to the xj variable. Note that when f is scalar, the Jacobian of f is the gradient of f. Okay, that is pretty clear when f is scalar. That is, when f is a single value, then the Jacobian will be straightforward the gradient. Okay, and now also note that the scalar x is allowed. Also, there is this is just a differential x. So if you want to just x is a scalar means x only has one value. Okay, that's your whole equation. It's just made up of like one variable. And then in that case, you're directly doing a differentiation. So it's no more a partial differentiation. You're directly doing differentiation. And for doing that, you have already an inbuilt MATLAB function, which is named as DIFF. So DIFF is f comma x. If you want to find partial derivatives, you use Jacobian f comma x. F is the vector of functions and x is the variables you're trying to solve for. So for example, here you have given a question, Jacobian, this is a function. Your first function is x, y, z. Second function is y and third function is x plus z. And the variables you're trying to solve for is first is x, then is y, and then is z. So first you will have this function's derivative with respect to x. So that will be just y is it. See, y is it. And next you will have this function's derivative with respect to y. So it will be x is it. See, and next you will have with respect to z, so it will be xy. Now coming to the second row, it will be y the derivative, y derivative of y with respect to x. So that will be 0. Derivative of y with respect to y, again it will be 1. And derivative of y with respect to z, it will be 0. And so on, you will have the last row also for this function. Okay. So similarly, the same thing we'll be doing here. So give me a second. So this is a function. You have like a symbolic function. Symbolic function means here x and y are value, like are like variables whose like what do you say? You don't have a specific value to it. They are just variables in an equation. Okay. So x, y square, and the second function is x square plus x square multiplied by y square. And then you're telling Jacobian of f because f first function is there and the second row has a second function. And the variable you're trying to solve for is first variable is x and the second variable is y. So that is your Jacobian. So this will be the answer you'll be getting. That is this functions with respect to x means it will be 2x, right? And again, the next will be with respect to y, that will be 2y. So you have a 2x here and 2y here. Okay. And now this term, you will have to do it with respect to x. So that will be y square multiplied by 2x, right? You can just manually do it. So it will become 2x multiplied by y square. And this will become, when with doing it with respect to y, it will become x square multiplied by 2y. So that is this. Okay. There is a 2 always here. That is because, mm, yeah, this is x square. Sorry, this is x square and you have the 2y here. Okay. Yeah, the answer is right. You can just confirm if it is right. Okay. Now moving forward to the next question. Yeah, I'll give you 1 or 2 minutes. So the equation represents steady state energy balance for the jacket fluid in a diabetic CSTR, assuming there is no phase change. So you know for a jacket fluid, this is a temperature, this is thing equation, right? So UA, and then you have T minus TC. That's the difference between your jacket temperature and your reactor temperature, correct? So this is the option A. Now moving on to the next question. I'll give you 2-3 minutes, and then we'll discuss the answer. Please try to solve it to yourself. And yeah, if you have the answer, just let me know in the chat box. So what is the answer to this question? A diabetic CSTR has a flow rate of F is equal to 2 liter per minute, and the reactor volume is of 100 liters, and the inlet concentration Ca0 is 1 mole per liter, and the reaction rate constant is given by K equal to 0.1 per minute. And what's the steady state concentration of Ca? So we already know this equation for a first order reaction, right? So that you can understand from the reaction rate constant, what is the order of the reaction, okay? Now, what you have to do is, if you have all the values that is given, first you need to find the residence time. And the residence time is nothing but the volume divided by the volumetric flow rate. So here that will be, volume is 100 and volumetric rate is 2. So you will have 50 minutes as your residence time. Now it's a first order reaction. So you can just try and see like the K, the unit of K, from that you can figure out what is the order of the reaction. And there is a formula that relates the order, so the order M to the power of this units. Okay. Now, we will get the equation Ca equal to Ca0 divided by 1 plus K2, where Ca0 initial concentration that is taken as 1 divided by 1 plus K is 0.1 multiplied by 50. So you'll get equal to 1 by 6. So that is equal to 0.1667. So that will be closest to the option D. That is 0.16 mole per minute. Similarly, you could do for like the second order reaction or third order reaction or anything. So it's very important that you know the basic formula, the reaction rate equation, and how can you integrate it and like find the concentration. But you don't have to study it by heart, but understand like how to integrate it. Maybe at least like uh, for the nth order reaction, how do you do it? The basic formula, at least you can try and learn it and keep. So this is the next question. I'll give you like 2-3 minutes and then we'll discuss the answer. So the answer is in the diabetic CSTF for exothermic reaction, if the cooling capacity is insufficient, what is the likely outcome? So the answer is the reactor, when the cooling capacity is insufficient means if there is an exothermic reaction, it is basically ejecting the heat, right? So if there is no enough cooling water cooling capacity, what happens is the reactant's temperature keeps on increasing. And finally, it will attain a steady state, but that steady state temperature will be higher than what is usually there when you have a proper cooling arrangement. So the option A, that is a reactor, will reach a higher steady state temperature. A reaction rate will decrease, so now it has nothing to do with the cooling capacity. Now the concentration of reactor will increase. Again, that doesn't have anything to do with the cooling capacity. That the reactor will reach a lower steady state temperature. It said that the cooling capacity, there is no enough cooling that is happening. So the steady state temperature will be higher than what is usual. Okay, so option A. Now the next part, again, you can use MATLAB or else you can try to code it using, try to write the code in a pen and paper and just let me know once you're done. Any answers for this question? So the question is, consider a following set of equations and solve it using Fsolve in Matlab. Initial guess is 0, 0, 0, and you have three equations here. Okay. Initial guess for x1 is 0, initial guess for x2 is 0, and initial guess for x3 is 0. So what you have to do is you have to like code all three together in a single vector. And what you have to report is report the x2 up to four figures after the decimal. Okay. Now we'll try to see the code in MATLAB. So first we have the initial guesses 0, 0, 0, and then we use the function fsolve. So this is the function we are trying to call, and the function's name is my system. And you give the initial guesses, which is a vector of value 0, 0, 0. Now what happens is you are giving initializing these vectors to be all zeros. That is a function vectors to be all zeros. Then you enter the first equation and the second equation and the third equations. You have to enter it correctly. Okay. Now, once it's there, you have the answers in the solution. But remember that the solution will have three values. It will have x1, it will have x2, and it will have x3. Out of which you only have to print the second value. So how do you do it? You can do it by using fprintf, and this is a string parameter, so that is x2 is equal to. This is how you enter a value inside a string. Okay, so this is telling it has to be this percentage sign says that okay, there is a floating point, and point 4 means it requires four figures after the point. Okay, so that's what this means. It requires four figures after the data point, and it's a floating point. And then the solution to this numerical data gets printed in this position. Okay, I'll just run and show it to you. So here we have the equation is solved properly. Now we get x2 is equal to 0.4025. So exactly after the decimal points, you have like four figures, 4025. So this is how you can print using fprintf. And I'm sure that by now you know how this fsolve works, right? So do you have any doubts? If not, let us move on to the next question. Yeah, I'll give you 2 minutes. What is the answer for this question? So what happens to the steady state conversion of reactant A? The flow rate F is increased in a diabetic CSTR. Okay. If the flow rate F is increased, which means the residence time. Okay. The residence time is V divided by the flow rate, volume divided by the flow rate, right? So there will be, if there is a higher flow rate, it means that there is a shorter residence time. Shorter residence time means if there is a less reaction time that is there in the reactor for the reaction to happen, which means there will be a low conversion. So low conversion means, so that is the answer is B, the reaction, the steady state conversion of reactant A decreases. This is answer B. Now moving on to the next problem. So it's a numerical problem. Please take a pen and paper and try to solve it and let me know the answer. What is the answer to this question? So in a CSTR, we have a heat of reaction given as minus 50,000 joule per mole. So this is an exothermic reaction. And heat transfer coefficient U is given as 200 watt per meter square Kelvin. And heat exchange area A is 2 meter square. Now calculate the heat removal rate Q if the temperature difference T minus Tc is given as 10 Kelvin. So we know all these parameters, we know it's an exothermic reaction. So Q is nothing but UA T minus TH. Okay, so that is U is given as U is given as 200, A is given as 2 meters, and T minus TH is given as this one. T minus TH is given as 10 Kelvin. So when you multiply it, finally you will be getting 4000 watt as an answer. So that is a value of Q, UA T minus TC. Any doubts? Okay, moving forward to the next question. Which factor does not affect the heat removal rate in a diabetic CSTR? So the answer is the heat removal rate is given by the equation UA T minus TC. So this is depending upon the heat transfer coefficient, that is U. It is dependent on the heat exchange area, that is A, and the temperature difference between reactor and coolant, that is T minus TC. So all three, A, C, and D, these are the factors on which the heat removal rate is dependent on. So the answer is absolute temperature of the reactants. Okay, option B. Now this is the last question. So this is a nonlinear equation. We need to find the intersection of two circles. So here we have two circles equation. One circle centered at 2, 2, and the other circle centered at 3, 1. Okay. And then we have the r square both to be equal to 3 centimeters. So we have like r square given as 9. Now we have the initial guess 0.35 and 0.6. So let us look at the MATLAB code. So first we give the initial guess 0.35 and 0.6. And then these are some, as I even the last week I discussed that there are some optimum options. So every solver that you use, every inbuilt function that you use, there are some options that are extra that is available, which you can add if it is needed or not. So right now in my optimum options, I have added that the display should be off. So basically this command that is entered, that is equation solved and all those details, right? So this will not be printed. So that is what is meant by display off. And then I have xol as this is the solution. Okay. Apart from this, if you want to display the actual value at the solution, what is the function values, that also can be given by the fsolve command, just that you need to give additional variables to store it. So this you can go see fsolve, help fsolve, you can type, and then you can see what all things you can get it printed. So gives you the value at this solution point. And exit flag means there are several exit flags. Okay. There are 0, 1, -1, and all. 1 means it has converged. 0 means it has not converged. So it depends. Okay. So there are different exit flags that are available. Looking at the exit flag, you'll understand, okay, did it actually converge to a solution? Or why did it converge to the solution? All those things can be seen. For example, I can just show you help fsolve, and there are optim options. And in optim options, if you go, I'll just open the documentation for fsolve. So here, if you go down, see, instead of display off, if I print display iter, then it will be printing like different iteration, what is the function value and everything. Okay. So that is another option that you can enter. Now coming into the exit tab, I hope it is here. Somewhere. Yeah. These are the exit flags. So if you're getting 1 as the value, it means equation is solved and the first order optimality is small. Second means equation is solved, but the change in x is smaller than the specified tolerance, or Jacobian x is undefined. So that is why we got the solution. 3 means equation solved. So all the positive values means equation is solved, but due to multiple reasons. So the negative values means the output function of the plot function stopped the algorithm. Equation not solved. Okay, so all the negative values means equation is not solved. So the answer that you get may not be accurate. So this you can use in your coding also. You can just keep a track of the exit flag. So if exit flag is negative, it means that your solver is not giving a right value. So if exit value is positive, that is greater than 0, you can say that okay, the solver is giving you the right value and you can take it. Okay. So this can you can use in programs when you're trying to code like big programs, and you have to make sure that your solver is reaching to a solution, like a proper solution. Okay. Then you can make use of this exit flags. Now coming back to the MATLAB. Just a second. So now fsolve is there. We have the system, that is my name of the system is circle system. Then I have x0, which is the initial guess, and I also give all these options. Okay. That is OPTs, that is here. Now, I'm just printing it. The intersection point is for this initial guess is it has to be a decimal point. Should be there should be 6 figures after the decimal point, and there should be also have a 6 figures after the decimal point. It will print the first solution and then the second solution. Now going to the circle system, you have the first variable as x1, second variable as x2, and then this is your two functions that you're dealing with. Either you can give it like this in a vector, in a metric square bracket, or else you can directly give f11 is equal to this equation and f21 is equal to this equation, like we were doing it before. This also can be done. Okay, now let me just run this and just show you what the answer is. So the intersection point is x1 is equal to minus 0.136,197. Next two is minus 0.106339. Okay, I hope there is no doubts. So this week we discussed the CSTR problem and we also did some problems based on FSOL. So this was basically an extension of what we did last week. So next week I think we'll get more challenging problems. Any doubts? If no doubts, that's the end of the session and you may leave. And please join for next week Friday 8 p.m. lecture. Sorry, 6 to 8 p.m. live session. Yeah. Thank you guys. I'll be closing this meeting.